Hey, welcome to The Explainer. Today we're going to pull back the curtain on the system that makes pretty much the entire internet work, the IP address. Think of it as the digital postal code that makes sure every single thing you do online gets exactly where it's supposed to go.
I mean, have you ever really stopped to think about it? How does your phone, out of literally billions of devices, connect to the exact website you want? And how does that website's data find its way back to your screen and not someone else's?
Well, it all comes down to a unique identifier called an IP address. Just like a letter needs a specific street address to get delivered, every little packet of data flying across the internet needs an IP address to find its home. It's the absolute foundation of our digital world.
So, what's an IP address actually made of? To really get how this all works, we've got to start with the absolute basics, the fundamental language of computers.
It all begins right here, with the humble bit. This is the smallest possible piece of data in computing. It's just a simple on or off switch, a 1 or a 0. That's it.
Okay, so you take 8 of those little bits and you group them together. What do you get? You get a byte. Now we're talking. This is a much more useful chunk of information to work with.
Now, in the world of networking, you'll hear this 8-bit group called an octet. Don't let that throw you. For what we're talking about, byte and octet mean the exact same thing. And this little guy, the octet, is the core building block of an IP address.
So get this, a traditional IP address, the kind we call IPv4, is exactly 32 bits long. And how are those 32 bits organized? You guessed it. They're divided into 4 of those 8-bit octets we just talked about.
Now here's the really clever part. That 32-bit address isn't just one long random number. No, it has a 2-part structure. The first part is the network address. Think of that like the street you live on. The second part is the host address, which is your specific house number. It tells you both the neighborhood and the exact house.
All right, so we know an address has a network part and a host part. So how did the early internet pioneers organize them? Well, their original solution was something called the classful system.
And this slide lays it out perfectly. The system created different classes, A, B, and C, just by changing where the dividing line was drawn between the network part, that's in blue, and the host part, in green. This simple trick allowed for networks of vastly different sizes.
Class A addresses used only the first octet for the network ID. This meant there were very few Class A networks, but wow, each one could have millions of individual devices. These were for a few gigantic early internet organizations. Class B was a more balanced approach, splitting the 32 bits right down the middle. It used the first 2 octets for the network and the last 2 for the hosts. Perfect for big companies and universities.
And finally, you had Class C addresses. These were for pretty much everyone else. They used 3 octets for the network, leaving, as our source material puts it, only 1 measly byte remaining for the actual devices. This meant you could have millions of small networks, but each one could only have up to 254 devices.
But you can probably see the problem, right? This class system was incredibly inefficient. If your company needed 300 addresses, you couldn't use a Class C. You had to get a Class B, which gave you over 65,000 addresses, leaving thousands to just go to waste. This, combined with the explosion of the internet, created a huge problem. We were running out of addresses, fast.
The solution is IPv6, the next generation of internet protocol. It was designed from the ground up to be the answer to what everyone knew was an inevitable, looming address exhaustion crisis. And this visual just shows the sheer scale of the change. We didn't just add a few more bits, we quadrupled the address length from 32 to 128 bits. This isn't just an update, it's a complete overhaul of our digital address book.
So the number of new addresses this creates is, well, it's almost impossible to wrap your head around. It's 340 undecillion. That's 340 trillion unique addresses. To put that in perspective, you could assign an IP address to every single atom on the surface of the Earth and still have enough left for 100 more Earths. Yeah.
Now, I know what you're thinking. That new address format looks incredibly long and intimidating. But thankfully, there are some simple rules baked in to make them much more manageable.
Take a look at this typical IPv6 address. It's made of 8 16-bit blocks, separated by colons. It's long and it's got a lot of zeros. But we can compress this. Easy.
You only need to remember 2 simple rules. First, you can drop any leading zeros from a block.
And second, you can replace one continuous string of all 0 blocks with a double colon. Just remember, you can only use that double colon trick once per address.
So, if we apply those two rules, we can take that long, clunky address and compress it into this much cleaner version. It is the exact same address, just written way more efficiently.
Just like the old system, IPv6 has special addresses. For example, the loopback address, which a device uses to test its own network connection, was 127.0.0.1 in IPv4. In IPv6, it's been streamlined to just a double colon and a 1. So much simpler.
These core ideas of having reserved addresses for testing or for broadcasting to all devices are foundational concepts in networking. They carry over directly from IPv4 into this new, vastly expanded world of IPv6.
So the crucial takeaway here is that we've made this monumental leap from a system built on scarcity to one of almost unimaginable abundance. This isn't just about keeping the internet running, it's about opening up a future for trillions of new devices, creating a connected world we're only just beginning to build.